Probability is essential to statistics in that any conclusion that we come to is not 100% sure. We have a certain degree of confidence in our solutions when we do inferential statistical tests, and probability will allow us to quantify that degree of confidence. Also, we're going to see that probability has plays a role in samples and the variability of samples, and we'll see how that goes into conducting inferential tests in terms of what's called a sampling distribution. But first, we need to get a good handle on probability and how you determine probabilities of different events. So first, let's start off with some terminology here. Your experiment is whatever process that you go through to get an observation or a result, and your outcome is a result of an experiment. The sample space is the set of all possible outcomes, and then an event is just going to be a subset of the sample space. So that's some of the outcomes. And then the probability of an event refers to the long-term relative frequency of that event, and we'll write it as P parentheses A, where P stands for probability and A is the name of our event. We'll notice here that the probability of an event A is always between 0 and 1. So probability is talking about chances of something happening. You can't have negative chances. And 1 is 100%. You can't have more than 100% chance of something happening. If probability of an event A is 0, that event is impossible. If the probability of an event A is 1, then A is certain to occur. Equally likely means that every outcome has an equal chance of occurring, like when you flip a fair coin or roll a fair die. And then we'll define theoretical probability of an event with the following formula. Probability of A, it's P parentheses A, is the number of outcomes in the event A divided by the number of outcomes in S, which is the sample space. So S is a sample space. So we can shortcut that by saying it's desired outcomes out of total outcomes. That's at least when we have an equally likely sample space. So this formula applies only when the outcomes are equally likely. So let's look at an example here and apply some of our terminology. So we roll one fair die. That's our experiment. What is an outcome? So an outcome is a result of rolling a die. So for example, we could roll a 6. That would be an outcome. What's the sample space? So sample space is the set of all possible outcomes. So you could get a 1, 2, 3, 4, 5, or 6. So our sample space is the set of those 6 outcomes. Is the sample space equally likely? Well, this is a fair die, so it should be equal chance of rolling each side, so that should be a yes. And then what's the probability of rolling a 2? Well, our event here, I've abbreviated our event by putting the number 2 in there, so this is going to be the number of 2's over the number in the sample space. Well, there's only 1 2 on a normal die, and there's 6 outcomes in the sample space, so 1 out of 6. Probability of rolling an even number, that's going to be the number of evens on the die over the total number of sides. That is the number in S. So desired outcomes are that you roll an even. There's 3 evens, 2, 4, 6. And then total outcomes from rolling a die, 6 possible. So you could leave that as 3, 6, or you could reduce it to 1/2. You can also write probabilities as decimals, so 0.50, or as percentages, 50%. These are all equivalent. Okay, and I do not have a preference for which way you write your probabilities, so you'll have to look at the context of the problem to see, and the answers to see what's most appropriate.